Hello students, welcome to Uncle. Good evening to all. Good evening, sir. Good evening, Arun, Amit, everyone.
Good evening, sir.
Good evening, sir. So we were discussing about effective mass. So today, first of all, we will calculate, or you can say we will derive the formula for effective mass, and then of course we will solve some numerical problems based on that. So in order to get the expression for effective mass, let us assume what is the velocity acquired by the electron whenever there is an electric field E acting on it. Okay. Suppose an electric field E acts on the electron 4 times dt, as a result of which the velocity acquired by the electron is dt. Okay. Let the displacement of the electron is dx. In time dt. Then change in energy of electron is given by, what will be the change in energy of the electron? Let's call that dE, and it will be force into displacement. And force on the electron is minus E times electric field. Is it? Can I write this dx as v dt? Because velocity is dx by dt. So this gives us dx equal to v dt. Okay. Clear?
Yes, sir.
So initially it is velocity by electron is p or dv.
Yes, please. Nobody speaking today. What happened?
Yes, sir. Clear, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
It is equal to v. I have taken it equal to v. Am I audible, students?
Yes, sir.
Yes, sir.
Velocity is v, Arun. Time is dt. Kindly read it carefully. Okay. Velocity, sorry for that. Velocity, it should be v. Time is dt, velocity is v. Clear? Now, yesterday, we calculated that velocity is given by this expression. So, substituting for v in 1, we get minus EE by h cross dE by dk dt. Is it? So, dE dE will get cancelled. No? dE dE will get cancelled. And from here, dk by dt will be minus EE by h cross. Kindly number it as number 3 equation. Is it clear?
Yes, sir.
Up to equation number 3, any doubt?
No, sir.
Yes, Beta, please speak up.
No, sir.
Sir, do we consider the electron as a wave or a particle in this situation? Hello, sir.
I think we are not audible to, sir.
Yeah, I guess. Hello, sir.
Are you people speaking?
Yes, sir.
Yes, let's type in the chat box first.
But your voice is not audible. What happened? Let me check. Let me check. One minute. So I was using headphones earlier, so that might be the problem, I think. Because I thought nobody's speaking. Now please speak up, anyone?
Yes, sir.
Hello, sir.
Yeah, now it's clear.
Yes, sir. Sir, I was having a doubt. Sir, in this case, we are considering an electron as a wave or a particle
Obviously as a particle.
because we are using the wave vector, like the k is there.
Then what happens? There is nothing wrong with that, even if you are considering the wave vector, because yesterday we calculated the velocity of the electron using the wave vector only, using the dispersion relation. Every material particle it is associated with a wave, according to de Broglie hypothesis. But it doesn't mean that we are considering that as a wave. Okay? Clear or not?
Yes, sir. Not completely, but a bit.
What is the doubt still you are having?
Sir, actually, this sentence is pretty confusing. Like every particle is associated with a wave. Like what exactly that means? It is not completely understandable. That is the thing.
Have you studied a bit of quantum mechanics?
A bit of like a tip of the iceberg.
Do you know about wave packet?
Yes, sir.
What is the composition of wave packet according to you? What does it consist of?
Energy.
Wave packet means an envelope of waves, a lot of waves.
Yeah.
And we always associate the wave packet with the particle, na?
Yes, sir.
Isn't it? If you study quantum mechanics, you will see that we always associate wave packet with the particle. That is group velocity. You call that as group velocity also, na? The velocity of the wave packet. Group means lots of waves. The velocity with which all the waves they are traveling. That is called group velocity. And the velocity of the individual waves, that is referred to as phase velocity. You might have studied about this.
No, sir.
So that's why this sentence is not clear to you. Na?
Yes, sir.
Are you in first year of your
No, sir. We have just started our SY.
Yeah, that is the reason. So you will be able to understand, don't worry, slowly. Okay, just keep this thing in mind that we always associate a particle with the wave packet, and wave packet means lots of waves, the group of waves. Okay.
Yes, sir.
So that's why this wave vector is there. Means we are making use of the dispersion relation in order to get the quantities. Now, this dk by dt is there. Now, what about the acceleration? Now, someone, yeah. Can you tell me about the acceleration? What will be the acceleration of the electron in this particular article? Acceleration of electron. Anyone? It's very easy.
Is it dv by dt?
Yes, dv by dt, because we have calculated the velocity, so it will be the derivative of velocity. And what is the velocity that we have? 1 by h cross. This we calculated yesterday. But now you see, this e is a function of k, na? Because in the dispersion relation, we are directly connecting e with k. Na? There is nothing like t. So can I write it like this by multiplying and dividing by dk? Can I do like this? And then it will become double derivative with respect to k. And this dk by dt, we have just calculated this value. You can see here, equation number 3. Please check. Clear? So now what will be minus EE according to you? It will be h cross square by d2 e by dk square. No? Please check. There should be a term containing there was acceleration on this side also. Na? I forgot to write one term, so there will be dv by dt. Or so you can simply write acceleration. That will be fine, I think. No need to write. What is this quantity? This is force, na? And we know that force is of the type mass into acceleration. So it means the mass, in this case, it is this quantity, and this is nothing but effective mass, and that's why I have put star as a superscript. This is the effective mass. And now you can see that effective mass also depends upon EK relationship. It will also come from that EK relationship. Okay. And now you will be further astonished to see the graph of variation of m star with k. So this is very important for you, this formula. You need to remember. M star is h cross square by t2 e by dk square. Clear to all? Yes, Beta?
Yes, sir.
Yes, sir.
Yes, sir.
Moving towards the graph now. Suppose this is k-axis and these are those inflection points, references, that k0 and minus k01. This is m star, okay? And let me draw the other lines also, the Brillouin zone boundaries. This is first. This is second. And the graph is like this. And now you will come to know why I was calling these k0 and minus k0 as points of inflection. Because you can see that the curve is changing its nature at these points. Earlier it was going up and then it is starting from below that k0, from the negative one. So it is changing its direction. So such a points, they are called points of inflection mathematically, when a curve changes its nature at a particular point. So this is the variation of effective mass with k. With k. So effective mass can be measured experimentally. It can be measured experimentally. With an experiment or technique, you can say, called cyclotron resonance. Cyclotron resonance. Okay, cyclotron resonance. So with the help of this experiment, we are able to get the effective mass of the specimen, and the formula for the same. Actually, we get that frequency. So that I will be telling you with the help of the numerical. That what is the formula to calculate effective mass? And now some important things regarding the effective mass in the actual band structure of solids. Now, every one of you will be knowing that there are bands in the solids that we have already discussed in the electronics. There are valence band, conduction band. You know, na?
Yes, sir. Yes, sir.
And normally in electronics, we have been drawing the bands as rectangular ones. We have been making the band diagrams like this. means we were making them as rectangular ones, means sharp edges. But in actual reality, the bands are not like this. They are the parabolic ones. These are the shapes of the band. And how I come to know about this? Because energy relationship is like this, no? Because E is proportional to K square. So it is parabolic in shape. Because the behavior of the electron changes, no? Because it starts slowing down. Earlier its speed was increasing, and suddenly it starts decreasing after crossing the inflection point. So that's why it is starting from that -1 and then going towards 0 slowly. That is the reason.
But sir, like mass, we have never heard of negative mass, like unlike antimatter that has negative mass that we consider. But in this case, what is it? Why is it negative? Like velocity, I can understand becoming negative, but why that mass is getting negative?
Actually, because of the interaction with the crystal, that is the thing. If the crystal would not have been there, then this would not have been negative. So because of the interaction with the crystal lattice, it is coming out to be negative. That is the reason. Because we have discussed yesterday that the electron inside the crystal lattice, it behaves totally in a different manner from the free electron. So don't consider it as a normal electron that we have. So this electron, it is totally different. Although it is an electron, but its behavior is totally different from that free electron. That is the reason. Or you can say that there are two kinds of potentials acting on the electron. And if one potential is greater, then the electron behaves in a different manner. And if the other potential is greater, then it's like this also. You can explain in these terms also. There are two kinds of potential on the electron. Can we say like this?
Yes, sir.
Please tell me. And what are those potentials?
Like, are you? Yes, sir.
You have supplied some voltage only, then the electron is moving.
Yes, sir.
We have given the field, and then there is a crystal field, and both are opposite to each other. Am I right?
Yes, sir.
Because if you place any specimen in the applied electric field, the developed electric field inside the specimen, it is always opposite to the applied one. Now suppose if applied electric field it is greater, then the mass of the electron, it will be okay. It will be positive, and we will say that the electron is behaving like a heavier particle. And similarly, a stage can come when the two masses, they will become equal. Two fields, they will become equal. Means the internal field, it is equal to the external field. Means the crystal field, it is equal to the external applied field. So what will happen in that scenario? Effective mass will become infinity. Because the total field will become 0. If total field is 0, the electron will not be moving at all. Means the acceleration is 0. So acceleration is 0. Now you see from here. Let me tell you. See here. This was the acceleration. Acceleration is inversely proportional to mass.
Yes, sir.
So if I'm saying acceleration will become 0, there is no effective field. So mass will be infinity.
Yes, sir.
So now if you make the crystal field or the potential greater than the external one, what will happen? Electron will start moving in the opposite direction.
Yes, sir.
So that's why the mass is negative, to take care of that negative sign, because it starts moving in the opposite direction as compared to the normal. Clear now? Still doubtful? No?
Yes, sir.
See, this is the field you have applied in this direction. Okay. So normally the electron will travel along this direction because it is a negatively charged.
Yes, sir.
And the crystal field is in this direction. Clear? So earlier I am assuming that this external field is greater than this crystal field. So electron was moving in that direction, so nothing wrong. So that's why its mass is positive. And it will be heavier also. And if the reverse happens, the electron start moving in this direction, what will you see? This electron is now behaving like a positively charged particle according to you. Na?
Yes, sir.
So now you will have to change its mass, na? Because you cannot change any other quantity. So that's why you are putting a negative sign along with the mass in order to define this phenomena, that now the electron is moving in an opposite direction.
So why can't we say that then the charge of that, we can't change the charge of that particle, like
How can you change the charge on electron? You cannot. Na?
because it is acting in the opposite way. So it is like more sensible to say that maybe it is acting like positively charged. So, but it is pretty weird to say that it is behaving like having negative
We
mass.
have said that, but because the things they have been developed in this manner, so that's why we are discussing those things. Na? We are not devising those things right now. So in the past, they have devised these things like this. They have taken the mass to be a variable quantity. So that's why we are varying the mass only. We are not altering the charge. That is the reason. Otherwise, also the charge could have been taken as the variable one, but they have done it like this. Because otherwise, the charge term, if you see, there is no charge term in this expression corresponding to a one electric field. Because you cannot say that the electron is chargeless. Otherwise, you could have said that the electron is a chargeless particle. So that might have been the problem with those people. That's why they have taken the mass as a variable. Okay.
Okay, sir. Sir, is it because like mass can be converted to energy, so we can consider it as to be variable, but charge we have never heard about like getting converted to some other thing kind of like that. So
yeah, you can also think like that. And there is another thing. Let me tell you why charge we cannot take as variable. If you study about special theory of relativity, in that charge is taken as invariant quantity. So if you take charge as a variable quantity, then we cannot transform the information from one reference frame to another, because charge is considered as an invariant quantity and mass is considered as variable according to special theory of relativity. So this goes according to special theory of relativity also when we take mass as variable rather than charge. So this is another factor, okay, that confirms this, or that confirms this point.
yes, sir.
You should have studied about this equation. I'm not by.
Yes, sir. We have
Yeah, sir.
yes, sir. We have studied.
So this says that the mass is variable, but you always say that the charge is invariant. So that is the reason. Clear now?
Yes, sir. But actually, there is still this doubt that that theory of relativity and these are classical theories, and the quantum things are like those are not those are considered as non-classical, right?
Yes. Yes. Then what is the next question?
No, sir. I mean, this is like the reason we are providing it is from the classical one, and the things mostly the equations which we are taking from those are from like non-classical theory. So
No,
that's
we
why.
are using the classical equation. Who is telling you that we are using quanta? F is equal to ma is the Newton equation. So we are using the classical mechanics in order to study the motion of the electron. We are totally dependent upon classical mechanics. We are not using anything like quantum mechanics over here. We are totally using classical mechanics. Kindly have a look at all the equations that we have used. We are using F equal to ma, na?
Yes, sir.
And from that equation you are getting the mass. So that is classical equation. Na?
But sir, those energy equations and all, and the you said the experiment related to the electron in a box, and also that was like kind of related to quantum mechanics, as you said.
Yeah, because the potential is acting on the electron. Na? So actually the things are related because we are comparing the electron with a free electron. Na? First try to understand the article. We are trying to compare the electron with that of a free electron. So that's why we are using that F is equal to ma and all equations. Because that is the only way to get the mass of the electron. Okay, so there is nothing like quantum equation which can give us the mass of the particle. So that's why the classical mechanics it is equally applicable, because we are making use of the classical equations. Otherwise, the results would have been wrong. If the classical mechanics would not have been valid on the motion of the electron, then the results they would have been wrong. But we are getting the correct results. That's why we are getting the effective mass. Okay.
Yes, sir.
So I was telling you that actually these bands they are parabolic in nature. And how do we come to know about this? Because E is proportional to k square, and this is the parabolic relation. Whenever one variable depends upon the square of other variable, it is parabolic, parabola graph.
Yes, sir.
So the curves or the band edges, these are called band edges. So that is the band edge of the conduction band. This is the band edge of the valence band. Okay. So now let me tell you one useful thing for your numericals. Suppose you are given two curves like this. One like this and other like this. And kindly name them as 1 and 2. So can you tell me which of these will correspond to higher mass? d2e by dk square is what? This is the slope. Na? So in which of these curves the slope is greater? According to you.
The second one?
In second one slope is greater. How?
No, sir.
I think first one.
The one which is more steeper, it is having more slope. Na? So clearly first one, it is nearly making an angle of 90 degrees. It is just coming straight towards the k-axis, whereas this is the slanted one. So one is
you asked about heavier mass or lighter mass?
I'm asking about the slope right now.
Okay. It's first one then, more slope.
Yes. So if the slope is more, the mass will be less. Na? If denominator is more, the mass will be less. Na? Okay.
Yes, sir.
So m star for 1 will be less than m star for 2. Clear to all? Okay.
Yes, sir.
So what do we infer from this? That the effective mass is inversely proportional to curvature. Isn't it? If the curvature is more, the mass is less. If the curvature is less, mass is more. Okay? Clear? And one more important thing. Another note. Near the bottom of the band. And bottom of the band corresponds to low K value. Near the bottom of the band, the electron behaves as a positive mass particle. Means the effective mass of the electron is positive. Near the bottom of the band means for small k values. And near the top of the band, electron behaves as a negatively charged particle. Negatively mass particle, sorry. Negative mass particle. Top of the band means high k values, or near the Brillouin zone, you can say that is the top of the band. Means, let me tell you, the variation is like this, na, that we have drawn. Oh, you can see from this curve also. See, near the bottom means near 0. You can see that the mass is positive. And near the top means near the Brillouin zone, you can see that the mass is negative. Clear, na? Please check. Is it clear?
So I understand the top of the band.
Top of the band means near the Brillouin zone edge. Top of the band means near Brillouin zone edge.
Okay, so at that point,
So it is negative, near the edge. And near the bottom means just near to k equal to 0. So it is positive.
yes, sir. That I got.
So let me tell you. Bottom of the band means near to k equal to 0. Top of the band means near the edge of Brillouin zone. Clear now? Is there? So let us solve some numericals based on effective mass. So now this is very scoring because it all depends upon one formula, and you just have to calculate the derivative, double derivative of E with respect to k. So the effective mass of electrons in the band, it is given by, if energy is given like this, and the options are Yes, please. Anyone? Yes, Divya, very good. Yes, sir. No, Amit, please check. Very good, Mamta, Ramdyal. No, Kanaya, I have calculated the double derivative. Please check. Very good, Tanya. So please check the derivative. I have calculated it for you. So now you just have to substitute this value. Yes, Satish, Yogita, very good. Abe, Ritika, Amit. So it is B option. Please check everyone. So kindly calculate the derivative carefully. Now, next one. In a crystalline solid, the energy band structure, that is EK relation, for an electron of mass m. This is from IIT Jam 2006. Please check it. Very good, Abhay, Divya, Siali, Arun, Siali, Himanshi, very good. अब सबका ठीक आ रहा है. Now see again, dE by dk. Actually, first we need to multiply, because there are two k's. So it will be like 2h cross square k square minus 3h cross square k by 2n. It's like this. So dE by dk, it will be like 4h cross square k minus 3h cross square by 2n. Then d2e by dk square will be like 4h cross square by 2n. Please check those who are not able to solve. Okay. Please, clear?
Yes, sir.
Now, another important formula, you can say concentration of intrinsic carriers or intrinsic carrier concentration in semiconductor. So formula is Ni twice of 2 pi kT by so these are the effective masses of electrons and holes, and Eg is the band gap. And these effective masses, they are different. Effective mass of electron and hole. This is band gap. The rest you know, Kb is the Boltzmann constant, T is the temperature. Okay. So what is the importance of this? So can I write this as, because everything else is constant, only these terms they are variable. So I have put all the constant terms equal to C. So you can write where C is equal to 2 times 2 pi k by h cross square 3 by 2 me star ms star 3 by 4. This is the C value. Please check. Clear?
Yes, sir.
So importance of this one is this, taking log on both sides. This one. So this equation is of which kind? Between log of Ni and temperature. What is this relation or behavior?
A straight line.
A straight line, simply. So which is the equation of a straight line? So let me plot this line now. So this is 1 by T and this is log Ni. So the line will be of this kind, and clearly the slope of the line, it is negative. That's why this line is coming down. See, the slope is this quantity, y is equal to mx plus c. Slope is negative, and from this slope we can get the information about the band gap, isn't it? Yes, please.
Yes, sir.
And now one important
Sir,
quantity.
please repeat it.
Yes, beta. Any doubt?
Yes, sir. Please repeat the last one.
See, this is the equation of straight line, and I'm plotting this one on y-axis and this one on x-axis, 1 by t. Na? So equation is y equal to mx plus c. So the multiplier of 1 by t, it will be the slope, and multiplier is eg by 2 kb with a negative sign. It means the slope is negative. Slope negative means the line is coming upside down. So it means from this slope you can calculate this band gap, na? Because kb is already known to us. It is Boltzmann constant, well defined.
Yes, sir. I got your point, sir. Thank you.
So do you know about Fermi energy? Do you know about Fermi energy now, or no idea? Okay, let me tell you that. But you might know about Pauli exclusion principle, because this we study in our 12th standard.
Yes, sir. We are acquainted.
So let me tell you with the help of that. So these are the energy levels. Okay. Of course, discrete energy level according to quantum mechanics. So according to Pauli exclusion principle, you cannot place more than 2 electrons in one level. One with upspin and other with downspin. It's like this, no?
Yes, sir.
So now there are always a finite number of electrons in any matter or medium or object, you can say. In any electronic system, there are always some electrons. No? So depending upon those number of electrons, we will go on placing them 2 electrons each in one energy level, and we will always end up getting some energy of the system. No? Whatever the temperature of the system may be. I'm talking about fermionic system. Electrons are fermions, this you know, na? Please speak up. You know this or not? Do you have any idea regarding the spin of the electron?
Yes, sir. That's clear.
Yes, sir.
What is the spin of electron?
Plus half and minus half. Like plus half or minus half.
Yes. So the particles having half integral spin, they are called fermions. Let me write. And this Pauli exclusion principle, it is applicable on fermions only. So we cannot place more than 2 electrons in one level. Is this clear now?
Yes, sir.
So now suppose you are having some fermionic system, means the system consisting of electrons in a simple way, and the temperature is 0. But there are finite number of electrons, so what we will do is, we will keep on placing 2 electrons in each level, and we will still end up getting the finite energy for the system. But this is against the classical mechanics, no? I think so. So classical mechanics says that, or you might have studied in statistical mechanics also, that at absolute 0, nothing moves. All the motion gets distorts at absolute 0, whenever t is 0. Have you studied this?
Yes, sir. That's clear.
Yes, sir.
But here you are saying that the system is having finite energy, even at t equal to 0. So if the system is having finite energy, it means something is in motion inside the system. No? If everything is stopped and nothing is moving, then from where the system is getting that energy? So it is against the classical mechanics. No?
Very much. Yes, sir.
So here the quantum mechanics comes into play. So this is quantum mechanical phenomena, the concept of Fermi energy. So now let me define the Fermi energy. So according to this, there must be some highest field level with the electron, and below which all the levels they are filled, and above which all the levels are empty. And suppose this is the highest field one. So then the energy of this level, energy of this, that is highest field level at 0 Kelvin, is called Fermi energy. And this level is called Fermi level. Is it clear now the concept of Fermi energy? Because number of electrons cannot be 0. No? So we will always have some finite number of electrons, whatever small the number may be. It may be only 2 electrons, but still that system, it will be having some energy. No? Clear to all? Yes, please.
Yes, sir.
And the formula for same is, kindly note down. And here n is the number density of electrons, means number of electrons per unit volume. And m is the mass of electron. So this is the formula for Fermi energy. And h cross is the reduced Planck's constant. Clear?
So its value is not equal to the usual h, right?
Let me tell you, it is actually h by 2 pi. So you have to divide h by 2 pi in order to get h cross. H cut or h cross is the name given to this. Okay?
Okay, sir.
Now, let us discuss something about Fermi level. So, position of Fermi level in a semiconductor.
Sir, that statement is true, na? That at 0 Kelvin, nothing moves, everything stops.
Classically, that is true. Quantum mechanically, that is not true.
How, sir? It just please give a glimpse of it.
Because of these number of electrons, we just said, na, that number of carriers. So, if the system is having some energy, it means the system is pretty light, na?
Yes, sir.
So it means everything has not stopped within the system. It means the particles of the system, they are moving.
Okay.
So that's
It means
why
there is still exchanging form.
I said that this is quantum mechanical result. It is not classical mechanics. It comes from quantum mechanics.
Okay. sir. That was wondered actually when I just heard कि वो true है तो ये true कैसे मतलब इसका भी कुछ तो निकलना चाहिए. Thank you.
ये classical में you may know that classically we have been taking the energy like this, na, kT.
Yes.
Now why we say that everything should stop at t equal to 0? Because the moment you put t equal to 0, the energy becomes 0 classically. Because classically we say
Yes.
that the system is getting the energy from the temperature. It is the thermal energy. But here the system is
Yes.
not getting the energy from the temperature. It is getting the energy because of this principle, which is forbidding the particles to enter into one particular state. So that's why they are entering into higher and higher energy state, and the system is gaining more and more energy.
Okay. sir.
So now, you might also be knowing this fact that in case of intrinsic semiconductor, this Fermi level, it lies midway at t equal to 0, of course. At t equal to 0 Kelvin, Fermi level lies midway. Is it clear? We always say this, na? But what happens with increase in temperature? With increase in temperature, where it will go, according to you? It will move down or go up?
Up, sir.
Up, obviously, it cannot go down. Na? Why? Because now, these electrons, they may be gaining some energy because of temperature, and they will start going into higher energy levels, which were empty otherwise. Okay? Clear? Because now the temperature is not 0. Na? I said with increase in temperature. So if the temperature is 0, so then the electrons, they will be gaining this energy, kT. So if that energy, it is more than this gap between the two levels, the electron will jump from the lower level to the higher level. Is it?
Yes, sir.
Fermi level will move up. And the relation for the same is, and this is the formula to calculate the displacement. So these are the effective masses of hole and electrons. EC is the energy of conduction band, energy of the bottom of conduction band. Energy of the top of valence band. Please check. Is it clear? Any doubt to anyone?
No, that should be up.
1 second, please. Let me have some water.
So the bottom of the conduction band would mean the
Let me tell you. We always calculate the band gap as the difference between these two energy levels. Na? Bottom means this is the bottom.
Okay.
Or top means this is the top. So we always take the top of the valence band and bottom of the conduction band to calculate the band gap. Na? Otherwise, also there are levels within the conduction band and valence band. We could have taken the difference between any of the levels, but we are always taking the difference between the topmost band in the topmost level in the valence band and the lowermost level in the conduction band. Clear? Is it clear?
yes, sir. That's good.
No. What happens in case of n-type semiconductor? In case of n-type semiconductor, where will the Fermi level go? Anyone? This we have already discussed.
No, sir. Yeah, towards the conduction.
And I gave you the hint also there, or some shortcut also to remember this fact. What is the dopant energy level which is created in n-type semiconductor? What is that level called and where that is created?
Donor level. That's
Donor
clear.
level.
Created near the conduction band.
Yes, sir. That's clear.
So you will say that the Fermi level will go up. It is near the conduction band now. That's it. Okay. And in this case, the Fermi level, it is near to the valence band. It is always near to your dopant level, whether it is acceptor or donor one. Clear? Now, what happens with increasing temperature? In case of n-type and p-type, where will the Fermi level go with increasing temperature?
For n-type, it will be between above donor level.
No, you have to tell me with respect to the valence band and conduction band. Na? In both the types, please tell me according to the valence band and conduction band positions, whether this will go up or down. They will ask you in terms of this. Na? This position is given. Now, from this position, will the Fermi level move upward or downward? Yes,
Sir, upward.
we have discussed this thing. Kindly think about it. What is happening with increasing temperature? Anyone?
Bonds on being
So
open.
electrons are further moving up, going to the conduction band from valence band.
Electrons are increasing, sir. Electrons are increasing.
Only electrons are increasing. What about
Both charge carriers. Both
what
electrons
we have discussed then? If both charge carriers they are getting released, so what will happen to this extrinsic semiconductor? I told you in the very first lecture of electronics.
increase.
No.
So it behaves like a conductor.
How can it behave like a conductor? It is a semiconductor. So obviously we cannot change the property of the material. Na? Material will remain only semiconductor. it is becoming more and more intrinsic. With the increase in temperature, the contrast between the majority and the minority carriers, it is decreasing. Because minority carriers, they are being released. Of course, the majority ones are also released, but their ratio, it is decreasing. Now it must have come to your mind. We discussed there with the help of example also. Now suppose, let me tell you. Suppose number of electrons are 100 and holes are 50 in the beginning. And what is their ratio? Now with the increase in temperature, suppose 50 electrons and 50 holes are released. Because they are always released equally in number. No? With one broken bond, you get 1 electron, 1 hole. So now the number of electrons, they have become 150 and holes, they have become 100. Now what is the ratio? It is 1.5. Now instead of 2, now you are getting 1.5. So it is slowly moving towards 1. And if the ratio is 1, it is intrinsic. Isn't it? Please tell.
Yes, sir.
Yes, sir.
So what you can say is, move towards the middle of the band. Because in intrinsic, it lies near the middle of the band. So move towards the middle of the band with increase in temperature. And same is the thing about this. Whether it is N-type or P-type, in both the semiconductors, with the increase in temperature, this Fermi level, it moves towards the middle of the band. Yes, please, anyone tell me? Any
Yes,
doubt?
now it makes sense.
Clear, na?
You
So
have
now-
already told us, sir.
Yes, should I explain again?
No, sir. You have already told us.
Clear?
Yes, sir.
Okay, thank you, Beta. So now you have to remember all these things, that in case of intrinsic, at T equal to 0, it lies midway, and with the increase in temperature, it will move up a little bit, and in extrinsic, it lies near the conduction band in N-type, and in P-type near the valence band, and with increase in temperature, it moves. Because all the theoretical questions, they can be asked. Okay, and it is very confusing if you do not do these things with reasoning, with proper reasoning. Then it is just a cramming, and it becomes very much difficult to remember. Okay, so just associate them with a proper reasoning, as I have given one example to you. Okay, so just always try to associate an example with the result. So that is the easiest way to remember that result. Clear to all?
Yes, sir.
Yes, sir.
Now please answer this simple question then, if you have understood all this. Totally based on this one. A phosphorus doped silicon semiconductor it is heated from now please tell. Only in the chat box, okay? Arun, please check. Obviously, one of your answer is correct, but not the other one. Please don't annotate over here. No, Amit, please check. Yes, Abhay, it's correct. Samruti Shri, Ramdayal, Kanaya, Divya, Steve, please check. And Arun, please check again. Why you are altering the position of the dopant level? That I'm not trying to understand, Arun. Is there any change in the dopant level with the temperature? I don't think so. Yes, Ali, Tamya, Praveen, very good. You cannot alter the dopant level. Huh? Very good, Uzma. Yes, Ritika. So we have just discussed that in N-type semiconductor, whether it is N-type or P-type, it always moves towards the middle of the gap. So it is N-type. Phosphorus dope means it is N-type, and we are increasing the temperature. So Fermi level will move towards the middle of the gap. That's it. Clear?
Yes, sir.
Yes, sir.
Arun, clear now?
Yes, sir.
Dopant level position, it is independent of the temperature. It is the material dependent property. It is totally dependent upon the dopant material. Okay. So now temperature dependence of electrical resistivity and of course conductivity. Now, first of all, conductivity, it is given by this formula. It comes from microscopic form of formula J equal to sigma I. Tau is the relaxation time or mean Boolean time. Is it? So
Yes.
we can see that sigma is directly proportional to this because everything else is constant. Na? Of course, m is somewhat variable, but that doesn't change too much. So sigma is totally dependent upon tau. And we know that mean Killian time, it is dependent upon mean free path. If the distance is less, the time is less. Okay. Clear? Please.
Yes, sir.
So now there are two kinds of scattering that is occurring. One is electron-electron and other is electron-lattice, or you can call them as electron-phonon. So when we study about lattice vibrations, we associate phonons as a particle associated with lattice vibration. Okay.
Yes, sir.
So what happens at high temperature? And this temperature is called Debye temperature. So this comes in Debye model of specific heat for solids. And this is high temperature actually. When we say T is very, very greater than theta D, high temperature, and room temperature is included in this limit. Clear? Please note down. So now either the electron can collide with another electron, or it may collide with the ions. Scattering with lattice means there are ions present inside the crystal. So electron can also undergo collision with those ions, and that is called scattering with lattice, or the electron phonon scattering. I think now it must have been clear to all of you. There are two entities present inside the crystal. Actually, it is just the temperature. It comes in Debye model. Because otherwise, if I start explaining the model, then it can itself take at least 1 hour. And there is no point of discussing that model just because of one name, because that is not in syllabus and that is going to take a lot of our time. It is just a temperature. Means it is material dependent. You can remember that this is different for different materials. Okay?
Yes, sir.
This all comes in specific heat chapter you can study from your BSc final year book. Now I don't know that in your university that subject is being taught in second year or third year or whatever. So this comes under solid state physics or condensed matter physics. Okay, in the chapter on specific heat, lattice specific heat. So electron can scatter with lattice or with other electrons. So tau is limited by two factors here. That is electron phonon. The one with the lattice has been named as electron phonon and the other as electron-electron. And because we are discussing high temperature, at high temperature, electron phonon scattering is dominating. And why it is dominating, I will tell you. I will try to visualize you somewhat. So in this case, inversely proportional to temperature. So as temperature increases, tau decreases. And then there will be more frequent Killians. So sigma is proportional to T inverse. If conductivity is inversely proportional to temperature, then the resistivity will be proportional to temperature, because conductivity is inverse of resistivity. Now let me explain you why it is happening. Suppose this is a piece of metal, you can say. These are the ions present at their respective positions. Now with the increase in temperature, these ions, they will vibrate more and more frequently around their mean position. This is what temperature does to any material. And there was an electron that was moving along its path. Now what will happen? If the vibrations, they are of large amplitude, then there is large probability of electron getting collided with this ion, isn't it? Please tell. Suppose the temperature is less. If the temperature is less, the ions will vibrate with less amplitude. Then there is less probability of electron getting collided with this ion. It can simply pass through this, or sometimes it may collide with this. But if the amplitude of vibration is large enough, then there is more probability of electron getting collided with this. So it means at higher temperature there will be more Killians. If more Killians means mean free time will be less, because more Killians are there. Is it okay now?
Yes, sir.
Yes, sir.
Clear to all?
Yes, sir.
Now second case. What happens when T is less than theta D? Means low temperature now. So at low temperature, both are important. So this is the dependency due to phonons. Okay. And due to electron-electron, it is 1 by T square. So in totality, sigma is inversely proportional to T5, or rho is proportional to T5. Because total resistivity, it is written as rho I plus rho T. This is impurity dependent resistivity. and this is temperature dependent. So impurity is getting affected because of two factors. One is the temperature and other is the impurity. So it means if we have a plot of resistivity, then we can get the information about the impurity content because it depends upon the impurity concentration. Okay, clear?
So can you repeat the last one?
Total resistivity.
Yes, sir.
I'm making a graph for this. That will give you better understanding. Actually, I will be making two graphs. So if the metal is pure, then impurity is missing. Na? So for the pure metal, it will be like this, simply. Because it depends upon T power 5 like this. So curved will be there. So you can write here. And here is the resistivity. Now what happens for an impure metal actually? For impure metal, some impurity content will also get added. So earlier at T equal to 0, this resistivity was 0. But now because some impurity content is also added, so it will start from some positive value like this. Please check now. Rather than being 0. And this is the impurity resistivity, contribution due to impurity. So this gives us the idea about the impurity of the metal. Clear?
Yes, sir.
Yes, sir.
So this was all about this solid state physics student.
Sir, I have a question.
Yes?
It's a bit related and a bit unrelated too.
Yeah, you can ask it.
So, sir, actually, when we have temperature higher than 0 Kelvin
Yes?
in intrinsic semiconductor,
Yes.
there are some electrons in the conduction band.
Yeah.
But the energy that is
Electron.
available around,
You are talking about the intrinsic one?
yes, I'm talking about the intrinsic.
Okay, then.
But the energy available around us is KBT, and that is not enough to break the bond between atom and electron. So what is the mechanism that is occurring there? How is they are giving up the energy? How the phonons are being transferred between those electrons? How is it happening? Means mechanism. How can I imagine that?
No, no,
They are pushing each other and pulling.
Are you asking about the carrier concentration? But you are mixing the phonon along with that. So I'm not trying to get it.
Actually, I have done a lot of work on this topic. Now that's why I'm using so many terms.
Now see, semiconductor is a different thing. If you are asking about the semiconductor, then there are electrons and holes. So they are getting,
Yes,
the, they are getting the energy from temperature, and by gaining that energy, they are breaking the bonds. That's why they are coming out.
Yes, sir, but the actual energy is present atom is not enough to break the bond. No? KBT is 26 degrees or some 26 matlab 300 degree Kelvin. That is not 300 Kelvin is not enough to break the bond between them. So, and the basic phenomena that is that they are vibrating actually, and that vibration they are giving energy to each other, and that from that
Yeah.
energy they are gaining energy and they are moving out of.
Yeah, that.
Now I want to imagine how they are giving up that energy.
Yeah, that
At
comes
room
from the temperature only. Na? And again, because the electrons they cannot have zero energy. That is another. Actually, there are lots of things that are going in there. So that's why
Exactly, sir.
that's why they always say in simple terms that they are gaining energy from the temperature, because temperature is the main culprit behind it. So that's why they say like this. But otherwise, it is very much complicated just to understand at this level.
That's what I was working on when I was in MCA.
Yes. Then you should have known about this. That everything is very complicated. It's not so simple as it appears to be.
Yes, sir.
That's why you would be having something to study in your PG. Na? That is the reason that physics is not getting finished in your UG standard. That is the reason. Okay.
Okay, sir. Okay.
Usma, there are sufficient questions regarding to these topics in the identical material because you are having volume solved also or the topic wise. So they are more than enough. But otherwise also we have done lots of questions in the class related to various topics. But if you still have any doubt or anything like that, then you can always discuss with me. We can discuss more questions in some special kind of lecture schedule for the special questions. Okay.
Okay.
Okay. So that's all for today, students. So this solid state physics part is finished. But kindly read about it. Kindly read every single topic. And if you still have some doubt, then kindly let me know. Okay. Because tomorrow onwards we will start with electricity and magnetism, and if you don't read these things right now, so then you are leaving behind those things, then later on you will not be able to understand these things in a better manner. Okay, because abhi to beta fresh hai na, because we have just finished these things, so it will be better for you, and try to solve the numericals related to these topics. Clear?
Yes, sir.
Okay, students, bye bye, take care.
Thank you, sir.
Thank you, sir.